So you ready? Okay. Well, hello everyone. Welcome to the afternoon session here at Tandy Assembly. I'm joined here by my two co-conspirators, Lawrence Kesteloot and Matt Boytim. And we wanted to give you an update on TRS-IO++. So the project we have been working on for quite some time, and we dubbed it the Swiss Army knife for Tandy enthusiasts. And hopefully then as we go through the presentation, you will understand why we chose that title. I'm going to give a very quick overview of TRS-IO++. Then Lawrence is going to do a live demo, which can be dangerous, but we'll give it a shot. And then we'll follow up at the end with some technical details behind the scenes, so you know a bit more on what's happening and how it happens. Can you flip the slide? So maybe it's a quick history. So I came here to the very first Tandy assembly back in 2017 in Chillicothe. Since then they moved here to Springfield, but quick timeline here. So initially we were just doing software, the Retro Store, which is basically a cloud-based service mimicking the App Store except for retro computing. So we're hosting CMD files in the cloud and you can browse and download them in real time. And we'll give a demo of that also later. But in starting from 2018, we also began doing hardware. So basically components that can connect to a computer and mimic basically some I/O capabilities. In 2020, I did something what I call higher, better.
Yes.
Okay. Oh, sorry. 2020, I did something what I call pocket TRS, basically just a little tiny PCB that mimics a complete TRS-80 Model 3, Model 4. So TRS-IO++ basically is coming full circle in the sense that it is now one board that combines everything. So it combines TRS-IO for the Model 1, for the Model 3, and also pocket TRS. So I want to give you, show you a picture of the PCB. Next slide. So that's the board, and for reference here, that's the size of it. So that's what it looks like in real life. I want to walk you through some of the components of the board. So there are two components. So there's an ESP32 microcontroller that's on the right side. The center, what is circled there, is Tang Nano 20K FPGA. So the ESP32 and the FPGA work in tandem to realize all its different functionalities. The ESP32 has Wi-Fi, which is really cool, and we'll also use that during the demo. Okay, next. Now the important thing is this little dip switch on the top left corner. It has like 4 dip switches, and that is how you can configure what you want this board to be. So since it's a combination of TRS-IO for the Model 1, Model 3, and pocket TRS, it can run a whole bunch of different modes. And I have a table later on that shows you, depending on how you throw the dip switches on, what it's actually doing. On the top side, you have both a 50-pin and the 40-pin connector. So you know the Model 1 has a 40-pin connector, the Model 3 has a 50-pin connector. And since it can emulate both, we're making use of both. Of course, at any point in time, only one of these two interfaces is active. So either if you configure it in Model 3 mode, it will only be, you use the top left, and if you configure it in Model 1 mode, it's going to be on the top right. Now, just also to mention this card can be connected to an old computer, or it can act itself as an old computer, and you can attach peripheral to it. So depending on the dip switch configuration, again, you can either have this board pretend to be an external hard disk. It can connect to a Model 1, Model 3, or you can tell it to be a Model 1, Model 3, and then you can connect some vintage hardware to it. Okay, next slide. So there's a PS2 connector that's for the keyboard. So if you run it in pocket TRS mode and you have to enter commands, and you can use a PS2 keyboard. Next one. There's an HDMI connector for the video output. So in pocket TRS mode, it just generates the output on HDMI. It also routes the audio to HDMI. Go back one slide. So if you run this in TRS-IO mode model 1. So basically you connect this guy here to TRS-80 model 1. It also snoops the address bus and it intercepts pokes to the video memory. And then the FPGA creates also video signal. So basically if you have an old model 1 but you don't have a CRT monitor anymore, you can use TRS-IO card to then just use it to create an HDMI signal. There is 3.5 audio jack. You can use it for audio output, although the audio is also routed on the HDMI. But one thing I'm proud of, and it gets back to one thing that Steve mentioned, we can also do input. So you can actually play an audio signal, a WAV file, and you can do see load if you're in pocket TRS mode, and you can see the flashing stars in the top right corner. Next slide. There's a micro SD card. So TRS-IO is compatible with the FRET. So you can just pop in your regular FRET SD card, and it does all the FRET thing. We'll also show that in the demo later. And last but not least, there's a PMOD connector. So that was, I think, invented or created by Digilent. Right? Am I right? Yeah. And it's basically just like a mini expansion interface, if you think of it. It's just some I/O pins connected to the FPGA, and depending on what you run, you can do different things with it. And actually, here we have a demo on Lightbright that you can later on see when you visit our exhibit. So there are different things you can just create, little peripherals you can just plug into the PMOD connector. Okay, the last slide from me before I'm going to hand over to Lawrence. So just to highlight, so this is the table for the dip switch that I showed earlier. So you have like 4 dip switches, and if they're all set to off, all to 0, basically you're running the card in TRS-IO mode, which means in that case you have to connect the card to a real Model 1, real Model 3, or Model 4. Dip switch number 4 determines if you're running it in TRS-IO mode for the Model 1 or Model 3. So that depends on which of those 2 expansion interfaces, the 50 pin or the 40 pin, is going to be active. All the other configurations are pocket TRS mode. So if you flip dip switch number 1 to 1 and the rest to 0, then you get pocket TRS mode for the Model 1. So then TRS-IO++ behaves like a Model 1. This E at the end stands for whether you use the internal or external TRS-IO. So TRS-IO++ also includes FRET, emulation, and TRS-IO. So if you have it set to 0, then you're using the internal TRS-IO, so you don't need any peripherals. But if you wanted to connect some vintage hardware, let's say a hard disk, you would flip this one to 1, this E switch to 1, and then it will disable the internal TRS-IO, and it will basically just communicate with the expansion interface. So this will give you an idea on the different configurations. And with that, I'm going to hand over to Lawrence, who is going to give you then a live demo, and cross fingers that it works.
Hi. So, like Arno said, the TRS-IO++ can be the computer, it can be the peripheral, or it can do both at once. I've configured this one to be both at once, so it's a Model 3 with all the peripherals built in. I've got a PS2 keyboard. The HDMI goes into a capture card that shows up here. Because normally you would have this going to a display, but for this demo I just showed it to a capture card. So when you turn it on, it boots up like a Model 3 would, and you get the splash screen for the TRS-IO, and then it just boots up the Z80 normally. And it's a diskette-based system, so you get the diskette prompt. I can hold down break, and then I get just a normal Model 3. Sometimes the keyboard doesn't get initialized properly, so I have to reboot the whole thing. But you can hold down the break key and it goes into basic like you would expect. And then you get basically just a cassette-based Model 3. What's that? Yeah, the reset button is physically broken on this one, so it's going to be great. Okay, here we go. Okay. All right, so you can see that normal. Okay, but you want to do more than this. So you want to be able to, you can do all sorts of things. For example, you can configure all sorts of ROMs for it, and you can do all the other stuff. But to do that, there are two ways to do it. One is you have this like onboard configuration system that you can use, or you can hit it straight from a web browser. But to do that, you need to get the machine onto Wi-Fi. So you can see that it's blinking blue right here. So blinking blue means that it doesn't know what Wi-Fi to connect to. And the way that you configure it over Wi-Fi is that it serves up its own Wi-Fi hotspot. So you go over here and you select, hello? Why isn't it showing up? Here we go. Okay, so you select TRS-IO, and now you're connected to its Wi-Fi. And then what you can do over here is you can go to TRS-IO.local, which is a web page that it's serving. Do you know why it's not working? Yeah, I'm just going to restart it. Okay. Okay. Okay, so this is the website that's being served by the thing. And over here, you can go over here to the configuration, and you configure whatever Wi-Fi. Now, normally you would configure your home Wi-Fi or something. We can't do that here because the hotel Wi-Fi won't work. So Arno's serving a system from here, Wi-Fi base station from here. So you configure the Wi-Fi network, and when you hit save, the system reboots and attaches to that system. And then here you should get, soon enough, you should get a green light right here. Assuming it, no, it's red. Is your system still running? Okay, here it is. Green light. So then we can reconnect here to, I connect to Arno's system. And here it says it's connected and it's all set up. So now we're set up on the same Wi-Fi and we can do all sorts of configuration changes. Like for example, right now it says that it's 5 in the afternoon, so you can go over here and you can tell it the time of day. And when you go back here, it says the correct time. And it gives you all sorts of information here. And here you've got a tab where you can configure the ROMs, and you can choose from a bunch of different ROMs that are on the system itself. And for each one, so you can rename the ROMs, you can upload a new ROM and delete them and all sorts of things. So all the ROM manipulation is done by drag and drop. You can just drag ROM files onto this. And for each machine that you're emulating in Pocket Trace mode, you can decide which ROM you want it to boot. So right now the Model 3 is booting off of a stock Model 3. We can choose a different one, like we can choose, for example, this diagnostic ROM. And then I hold down the reset button for 5 seconds. And now I've rebooted into the diagnostic. I can also choose a ROM which is the Fred one. And on here there's a SD card which has 4 Fred images. So we have 4 Fred images on this SD card, and then because the TRS-IO is a full Fred emulator, it'll go through and look through the SD card and why isn't it?
Pushing the SD card.
Actually, hold on a second. Yeah, so the SD card. So this can be helpful to figure out what's going on. Okay, so mounted. Okay. And so you've got a virtual hard disk, which we've just booted off of, and you have all the other peripherals that I talked about. Like you could do network access. So one of the things you can run is RS client, which is RS's retro store. So this is the thing that Arno talked about, where there's an app store out there in the wild, and this is connecting over the network to get this list. So you can browse a list of files, and this is all being downloaded in real time from this thing. And this would work if you were plugging this into a real machine as in TRS-IO mode. It would look just like this. With a real, you could do it with a real hard disk, you could do it with a Fred, all this would work in all the different cases. So it downloads information about the games, it can download the actual game, and it just runs it. There's various things you can configure here, like for example, you can go back and change the color of the virtual display, if you want to do that. Oh yeah. Yeah, there's audio. Okay. The way that you typically get things into Fred images is that you have an SD card or something, and on the SD card is the Fred image, and you can put like another file, the file you want to import, onto the SD card, and then you launch the Fred image, and then you run the import/cmd command, you specify the file name, and it copies it off of the SD card onto the Fred image, or you could do export the other way. So it's a little bit clumsy because you have to do things on the SD card and everything. So Arno wrote a program called Xfer, and it uses the TRS-IO system to listen to ports, and then the web page contacts that directly, and then it can do all the commands remotely. So here when you refresh, it gets a directory, and you get a directory of the hard disk on your web page. Notice in the upper right here, it's a good thing that Steve didn't patent the two blinking lights, so I can use this thing as a progress bar while it's happening. So here you can do all the normal operations. You can drag files into this thing, you can rename files, you can delete them, you can re-download them so you can get files off your hard disk. Again, this would work with a physical hard disk. Let's try uploading a file. And the Xfer program shows you what is happening as it's happening, so you get a sense of like the files being sent back and forth. Here I'm uploading a high-res graphics demo program. So there it is, HRG tests. And this also shows off that the TRS-IO emulates the Tandy high-res card. What's that? Yeah, it just takes so much time. Okay. You know, I want to reboot again and show one last thing, which is that the TRS-IO will do orchestra 9D emulation. Did you turn it on? Okay. Okay. You get the idea. Okay. Enough of that. Okay, actually one more thing. The last peripheral that okay, so Pete wrote this program in BASIC, which uses the networking aspect of TRS-IO. So it's just a simple program that hits the whois server, and it's getting this live information. So so if you have one of these, you could just write a program in BASIC or in assembly language or whatever to hit the network. And the last peripheral that we emulate here is a printer. So there's a virtual printer on the web page. So if you're back here and you type list, it comes out here. And you can save it as a text file and so on. So it's the virtual hard disk and the network and orchestra and the high-res card. And that's the demo. So, thank you.
So, hello? Can you, I think I'm not, test. Try again, hello, test. Can you hear me? Little. Well, I'm a teacher, so I can maybe raise my voice, but just to be sure, so the demo you just saw configured the TRS-IO++ cards in Model 3 mode. So it behaves like a Model 3, and it has an internal TRS-IO fret that it accesses. That's how it could do all the fret stuff. Now, if you flip the switch and you turn it into a TRS-IO mode, you can connect it to a real Model 1, Model 3. You can do exactly the same demo. So everything that you've seen here, from the virtual printer to fret, everything would just work in reverse, but then booting off from a real machine. Can you go back to the slides, please? So we wanted just to, yeah, I didn't have time to make a nice slide, so excuse my hand drawing here, but I ran out of time. We wanted to just do some, explain some technical details of TRS-IO++. The first thing I wanted to mention is here the interplay between the ESP32 and the FPGA. So the FPGA does not have enough memory to do everything, so you cannot have like one big FPGA bit stream that can do everything. So we had to break it down and create different bit streams for the different modes, like one bit stream for the Model 1, for the Model 3, for the Model 4, for TRS-IO. So what happens, and this is kind of the flow chart here, so when the ESP resets, it queries the dip switch to find out what does the user want. Then it queries the FPGA, what is currently running on you. If it's the same, then it's fine. It can just go and continue. If we don't have the correct firmware on the FPGA, then the ESP is using the SPI interface to upload the correct firmware to the FPGA. And then it uses JTAG to reset the FPGA so that everything is seamless and just happens automatically. So the LED will turn blue during that time. So every time you choose a different configuration on the dip switch, it will need to upload a different firmware. It takes about like 30 seconds where the LED is going to be blue, and then it will just upload the correct firmware. What it does then is it will go and check is the board configured in pocket trace mode. And if yes, it is going to upload the correct Z80 ROM. So what Lawrence was showing earlier. So if you have like the Model 3 ROM with a fret patch enabled, or if you just want to have diagnostic ROM, so that's what happens there. It also is being uploaded by via SPI. So all the FPGA firmware images and also the ROM images are all on the ESP's flash. So there's nothing that happens online here. And at the end here, the ESP resets the Z80 and then it just starts running. So that is just kind of to explain a little bit the interplay between the ESP and the FPGA. Next slide. I couldn't find a better way of explaining that. So I just wanted to explain the XFIR thing that Lawrence showed earlier. So how you use that web interface to basically import, export files onto the LDOS image that you're running. So on the left side, you have the machine, or in this case, our machine emulation in pocket trace mode. You have the Z80 on the bottom, you have the operating system LDOS running on top of it, and then there's something I call TRSLib, which is basically a C-based library that gives you a nice, clean C API to the machine and to LDOS. And on top of that is the CMD that Lawrence launched earlier. It acts as a server, and it sits on the machine, and it just waits for commands from TRS-IO. So this little dotted ant line thingy is basically how a request goes. So you have the browser on a different machine on the far right. Via Wi-Fi, it connects to TRS-IO. The browser makes a request. TRS-IO relays that via the expansion interface, so the in-out interface, to the Z80. It relays it up to the XFER application. Then XFER is making, via the help of TRSLib, calls to LDOS. So, like for example, getting the directory listing. So then XFER, with the help of TRSLib, makes down calls to LDOS to get the directory listing. It goes up again to XFER. It parses the whole thing as a little package, and it sends it back down again to TRS-IO, back via Wi-Fi to the browser. And then the browser interface renders this then in its interface, as we have seen in Lawrence's demo. So that's basically how the interaction works, how you can very easily manage your thread images and files that you have on the LDOS hard disk image, then just using a browser interface. You know. And you can just hit escape in XFER, and you come back to the prompt. So that's the two little technical things I wanted to explain from my side, which is kind of an update from last year. So you remember we had also a preliminary TRS-IO++ presentation last year, but that's kind of the new stuff that happened since last year's Tandy assembly. I'm going to hand it over now to Matt, and he's going to talk about the FPGA part a little bit more.
Yeah, so my contribution in all of this is primarily the FPGA, and this is an overall architecture diagram of what the TRS-IO looks like. You have the ESP, or the TRS-IO function, which is implemented primarily in the ESP32 module. And then the hardware interface portion is implemented in the FPGA, and then all of the hardware-specific peripherals like the display and the high-res and those kinds of things are implemented primarily in the FPGA. And then it operates into two modes, as we discussed. It operates as TRS-IO mode, in which case the real TRS-80 is external to the TRS-IO, and it operates in pocket TRS mode, where the TRS-80 is internal to the FPGA. So next. This just shows what the module looks like, the FPGA module that we use. I'm personally not a big fan of using kind of modular design. I really like to do chip-level design. But with modern FPGAs, it's just not practical. The average do-it-yourselfer is not going to place a 256-ball BGA package. So we're resigned to using some kind of a package like this. It's a great convenience, but to me, it's not my first choice. But it turns out to be pretty good. It has a high pin count, high FPGA density. It's worked really well in this application. And I use GoWin FPGAs in a lot of other applications as well. Next. So last year I explained how the FPGA has a bunch of resources. Clock resources, has gate resources, has memory resources, has DSP block resources, and so on. So when you're picking an FPGA, it's really based on what your application requires. And in this particular case, it turns out that the embedded block RAM is the limiting resource that drove a lot of the design decisions in the TRS-IO++ implementation. So what I did is I have this matrix which shows the different modes it operates in and the amount of block RAM that's required for those things. And in FPGA circles, you tend to refer to your kind of resources in terms of too little or too few, what they call slack. So generally when you design, you want to have a positive slack, which means you have excess resources. So if you go down through the VRAM slack column, you see in most cases we have excess slack, but there are certain instances where we have negative slack, which means those are not going to be implementable. And so we've made choices to make sure that we have positive slack in all the modes we want to operate in. But the GoWin has 92K of block RAM, so obviously you're not going to implement 128K Model 4 or Model 4P when you only have 96K of block RAM. So we've made some compromises, and you can see that in the Model 4 mode, we don't implement the high-resolution graphics because we don't have enough memory. And so we implement the Model 4P, and how that works to our advantage is that the Model 4P only has, I think, 4K of ROM. It only has a boot ROM. It doesn't have the full basic ROM. So that frees up 10K that we're then able to apply to the high-res function. And I didn't even detail the TRS-IO mode because that's a very small subset of the overall TRS-IO++ implementation. So we have definitely much greater than zero slack in that case. So next. So what I had outlined last year is we had planned on having these 5 major modes. We were going to have Model 1, Model 3, Model 4, Model 4P, and then a single TRS-IO mode that would work as both TRS-IO Model 1 and TRS-IO Model 3. Because there we weren't DRAM limited and we were able to do it, but since we already had 5 modes and it led to an overall simpler design, we ended up deciding to split the Model 1 and Model 3 TRS-IO modes into 2 designs. And as Arno explained, with the way the dip switches work, it's fully transparent anyway. You flip the switches, you wait a few seconds, and it uploads the image. And so it's really transparent to the end user, whether it's one design or 2. The decision to split it was kind of based on 2 things. As I said, it leads to 2 simpler designs versus one more complicated design. And the other one, kind of interestingly, is the splash screen. So during the demo, you saw when Lawrence turned on the TRS-IO++, it starts out in this splash screen. Well, we use the high-resolution screen if it's available for the splash screen because it just gives us a better-looking splash screen. But with the combined design, that was a problem because we end up sharing the memory between the Model 1 high-resolution screen and the Model 3 high-resolution screen. So we can't initialize that memory for both screens. We get one or the other. So the compromise was to use the high-resolution splash screen for the Model 3 because the Model 3 doesn't have a text screen, and then we would use the text screen for the Model 1 splash screen. And if you see the splash screens, the high-resolution one is a lot nicer. So when we split it into 2 designs, it allowed us to use the high-resolution screen for the splash screen in both cases. So anyway, just kind of a detail, but those are the kinds of things that lead to the design decisions that you made when you go through a project like this. I think is that the end? Oh, no. This is just kind of a reiteration of what Arno said. It just shows how the dip switches are used and the settings are silk screen on the back. And yeah, so you just, you decide which mode you want, you set the dip switches, you press the reset button, it updates the FPGA and then you're running in that mode. So the fact that it's 5 or 6 designs is completely transparent to the end user. I think that might be it. Yeah, so yeah, this is just kind of some future work, some things that have been discussed. So Arno has mentioned, so currently Extra works only under LDOS, so it would be nice if it was portable to the other DOSes that the Fred supports. And I think that's primarily a matter of making the library compatible. Over there, firmware update, I don't know really where that stands. I think that was in the original design, but it would be nice to be able to do a firmware update completely over the air. The PMOD module, so we have one currently, which is what I call the Light-Bright 80, which is this, kind of, it looks like an old-fashioned Light-Bright toy, and it's a memory visualizer, so it's kind of a gadget, but it's interesting and it's useful. But the PMOD is a kind of a flexible FPGA expansion standard, and it just gives you, it gives you essentially 8 GPIOs that you can use forever you want. So we've kicked around some ideas about doing some other things with the PMOD. The one thing in particular that you might want to do is if you mount the TRS-IO internal to a Model 3, then you might want to display the high-resolution graphics on the actual CRT. And you can do that, but in order to do it, you have to route the video signal through the TRS-IO so they can switch between the high-res and the text screen. So you can do that with a PMOD. And we haven't built it yet, but that's one particular PMOD that you might want. Another thing that you could do is you could replace the keyboard on a Model 1 with a PS2 keyboard because we have the PS2 connector. But you would need to build a keyboard interface to the Model 1 keyboard connector to do that. But that's another thing that you can do with the PMOD. The other thing is to be able to prepare a Fred SD card from scratch. So, currently, if you want to make a Fred SD card, you get all your files, you put them on your computer, you copy them over and so on. And once you know what you're doing, it seems easy, but for a first-time Fred user, it's not always so obvious, and when things don't work, is it me, is it broken? So Lawrence has the idea of having some kind of like a setup wizard where you would just plug in the SD card and it will prepare it so you can use it with TRS-IO. So I think that's the final slide. Okay, very good. So any questions?
Actually, one more.
Oh, one more? Oh.
I'm
Yeah, please allow me just to make a quick comments here because I feel like coming full circle here. Again, I came to the very first Tandy assembly and just started iterating over different ideas and expanding. I've always been an open source guy, so I do believe on putting my work out there for other people to tinker, and I just wanted to give credit to everyone who in some form or shape has helped make TRS-IO happen on what it is today. And many of those people are actually in the audience here today, so I just wanted to say thank you to those that have helped make TRS-IO++ is what it is. So with that, we can open it up to question. Yes?
Are they for sale and how much?
I do have a few extra ones. Just, we are on the far end of the corner here. Come, I have a few extra cards. Yes?
The dividing line between the ESP32 and the FPGA. If the ESP32 are mostly TRS-IO vertical logic is,
Yes.
and if you had a bigger FPGA in the future, then just when the ESP32 becomes superfluous,
So the question is again the difference between the ESP32 and the FPGA. So yes, you're right. The ESP runs all the TRS-IO stuff and FRET emulation. The FPGA is mostly, especially for pocket TRS mode, running the Z80 core and the machine emulation and HDMI and so forth. If we had a more powerful FPGA, the ESP would still be there. No, it has the Wi-Fi and there's a lot of C code that by now is in TRS-IO. So that you cannot just simply move over to the FPGA. So it will always be this tandem between ESP and FPGA. Other questions? Yes?
So, since you have the TRS-lib, did you write the expert program in C?
Yes. Yes.
And you compiled it on a modern system?
Yes. Okay, so Blair was asking about xfer, this little CMD file I was running on LDOS. So TRS-lib is a C library that allows you to write TRS-80 applications in C. And we're using an SDCC, the small devices C compiler that runs on the host, so it does not run on a Z80. But that is how I created the CMD file. So both the RetroStore client that Lawrence demoed and also xfer, they're both written in C, and SDCC creates an CMD out of it. Other questions? If not, then thanks for your attention, and come and see the demo at the end of the room here.